Hello, in this short video I'm going to investigate the following problem. Let S be a set and let a star be a binary operation defined on S such that for all x belonging to S, x star x equals x, and for all x1, y, and z belonging to S, x star y, then a star z equals to y star z, then a star x. Prove that the star is associative and commutative. Pause the video at this point and give it a try. Okay, so these two conditions are given to us about the binary operation star defined on the set S. We are supposed to show that this binary operation is both commutative and associative. If you don't mind, let me drop this star and use the product notation. So I would write this as xx equals to x for all x. And I would write this as xyz equals to yzx. And for understanding this better, if you don't mind, let me label these variables. So let me call this 1, and this 2, and this 3. Then 1 goes here, 2 goes there, and 3 goes here. Okay, so this means that if you have 2 and 3 together, and then 1, you can write 1 and 2 together, and then 3. Okay? Okay, so let me start proving the commutativity part first. So I would say that let alpha and beta be elements of the set S. My goal is to show that alpha beta is equal to beta alpha. Okay? Okay, so let us start. Alpha beta is an element in the S. It can be written as alpha beta multiplied by alpha beta. Why? Because we know that for every element in S, that element multiplied by the element itself, it becomes the same element. So if I take alpha and beta and multiply it by alpha and beta, it becomes that one. Now I want to give the role of label 1 to the whole combination here. I want to start from here. So 1, I want to give the role of 2 to alpha and give the role of 3 to beta. So then this tells me that 1 and 2 can be combined. So I have a pair of brackets, which is this one. 1 is this guy, so alpha beta, and 2 is alpha, and then 3 is beta. And I want to use this over and over again, okay? So what I mean here, I give the role of 1 now to this, and I will give the role of 3 to beta, and give the role of 2 to alpha. So 2, 3, 1, 2, 3, 1 can be written as 1, 2, 3. So what I will do, I would write it as 1, 2, and 3. And outside that, I have beta. But alpha alpha, because of the same condition, becomes alpha. So this becomes alpha beta. Yes, this is alpha, this is beta, and then I have beta. So be careful, I am not using associativity, I am using this rule. Okay? Now I want to give the role of the label 1 to this, and then 3 to this one, and 2 this one. So I have 2, 3, 1. 2, 3, 1 can be written 1, 2, 3. So this becomes beta alpha 1, 2, 3. Yes? And I want to do it once more by giving the role of 1 to this guy, and then 3 to this guy, and 2 to this one. So again, 2, 3, 1. 2, 3, 1 can be written 1, 2, 3. So this becomes B, beta, beta, and alpha. And again, beta, beta is just simply beta. So it becomes beta alpha. Now compare. You see, alpha beta is equal to beta alpha. So this means that my operation is commutative. Now that I have proven the commutativity, I can immediately prove associativity. So what is associativity? So let us have alpha, beta, and gamma in my set. I want to prove that alpha, beta, gamma is equal to alpha outside beta and gamma together. So that is my goal. I want to show that this is the case. Okay, so what can I do? So you see here, if I go up there, so here I have 1, 2, 3 can be written as 2, 3, and 1. Okay, so let me start from here by giving the role of 3 to gamma, and 2 to beta, and 1 to alpha. So alpha, beta, gamma which is 1, 2, 3 in that order, can be written as 2, 3, and 1. So I open a pair of brackets, 2, 3, yes, 2, 3, sorry, 2, 3, and 1. Okay, that's the case. Okay, but now we already showed that this is commutative. So this means that I can commute these two elements. So then it becomes alpha, beta, and gamma. So I am done. Alpha, beta in parentheses, and then gamma is equal to alpha times beta, gamma. So associativity is also proven. So I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.